Okay, welcome to Chem 141, General Organic and Biochemistry 1 at SUNY Broome Community College. I'm your instructor, Daniel Brennan, Dr. Brennan, Dan, whatever you like to call me. And I look forward to working with you this term on building an overview of general chemistry in particular, and then hopefully I entice you to stick around for Chem 142, where we'll hit more of the organic and biological chemistry topics. So Chapter 1 is all about chemistry and measurements, and we'll have 10 total little video segments on this, audio segments, whatever you want to think about these little mini lectures as. And so they'll all be on that theme of chemistry and measurement, but this first one is focused more on chemistry and chemicals. So people have heard those terms a lot. Actually, there's a fair deal of marketing research that suggests people like the word chemistry. It makes you think of good things, like good chemistry between actors, maybe on a film, whereas chemicals has a very negative connotation. Oh, don't drink that, it's full of chemicals. And hopefully, throughout the course of this semester, if you're not already well aware, everything is chemical in nature, and we'll do the best job we can do to help you understand more about harmful chemicals versus helpful chemicals, but really just being a chemical means you're stuff, you're matter, you're not nothing, and there's no such thing as a good chemical or a bad chemical inherently. It's the dose, how much of the chemical you're exposed to, and what the purpose is. Something that might be therapeutic in small amounts could certainly be toxic in large amounts. And some things don't have any immediate problems, like sugar, sucrose, table sugar is fine for us in whatever amounts we can consume in a given amount of time, but long term, obviously, it's not a good idea to have lots and lots of sugary snacks for many, many days or months or years without having to worry about some long-term consequences. So hopefully we're dispelling some myths, and there are definitely harmful chemicals out there, hazardous substances we should limit our exposure to, but there are also a lot of very beneficial substances like the food and drugs that we often take in on a daily basis. So first and foremost, we have to have at least a functional understanding of what chemistry is. Chemistry is probably the newest natural science. Physics, biology, geology, these go back thousands of years. Chemistry is only a few hundred years old. It's its own separate discipline, although certainly alchemy was pre-chemistry. And we're actually getting a little more in touch with our roots. A lot of the early 1900s, we were very much opposed to acknowledging alchemy's influence on chemistry. We wanted to distance ourselves. But now, in these 2000s, we've decided that let's embrace some of that. There was actually some really good science in alchemy. No, we didn't make the philosopher's stone or turn lead into gold, but a lot of early chemical concepts have their beginning in alchemy. So chemistry itself is a separate science. One of the physical sciences is the study of matter and its composition, structure, property, and reactions. Really, if you got to sum up chemistry in one word, it's change. We're looking at matter before a chemical reaction, and during a chemical reaction, and then after a chemical reaction. And in addition to the matter and the rearrangements that happen within that matter, we're also interested in the energy that accompanies those changes. So that's chemistry in a nutshell. It's tough to box chemistry in anymore because chemistry tends to expand into other areas. A lot of you are probably here for biomedical applications. That's one of the main reasons most students take chemistry, is because they either need it for biology or medicine or nursing or any of those allied health fields. And that's because chemistry is important. When your body stops doing chemistry, when you stop having those changes and the energy that accompanies those changes, you die. So chemistry is vital to life. So biochemistry or geochemistry or physical chemistry, there's lots of crossover in chemistry with other fields, and we really tend to be pretty high opinions of ourselves. We call ourselves the central science. So chemistry is often called the central science because it has an impact on so many areas, and chemists like to think of ourselves as pretty important individuals. So I'll try to keep the ego in check, but just beware of chemists. We like to think we can do pretty much anything because we really can. Now, I hope I'm not going out on a limb too far here, but I think maybe a few of you have some chemistry fears, chemophobia, a little anxiety about taking this course. A lot of people delay this until the last possible moment, and hopefully I'm here to show you that chemistry is everywhere. Chemistry is not anything to necessarily be afraid of. Yes, there's going to be some math involved. Yes, there's going to be some memorization and some problem solving, but once you realize that chemistry is all around, then maybe chemistry doesn't seem like this stuffy academic subject that unfortunately I'm afraid some of you have had some fears about. Instead, chemistry is everywhere and every day, and you're a result of some really interesting chemistry. The food you cook, the chlorine that cleans your pool, the food you digest, the reaction that happens if you have some heartburn and drop those antacid tablets into a glass of water. If you happen to like the ones that have the citric acid as well as the base together, you know that familiar fizzing that we see here on the screen. And this is all important, and this is probably why you're in the course, is because something you want to do at some point in your life is going to involve chemistry, and I'm here to make it as meaningful and as painless as possible. Okay, so within chemistry we have a number of different pillars of chemistry, actually probably 5 pillars of chemistry. General chemistry would often be subdivided into physical chemistry, inorganic chemistry, and then analytical chemistry. Organic chemistry and biochem would be the 4th and 5th branch. Actually, biochemistry became the realm of chemists while I was in college. When I was doing my undergrad, that's the year that the American Chemical Society decided that biochemistry is really us and ours and not the biologists. It's really the chemist field, and they added that 5th subdiscipline of chemistry. So in this semester, the general chemistry that we'll do, you'll get some experience with analytical chemistry when you're working those lab simulations through late night labs. You'll also get a feel for inorganic chemistry when we look at that whole periodic table and we talk about the metals, the nonmetals, and the metalloids, or semi-metals as they're often called. And finally, physical chemistry tends to be when we're doing that mathematical problem solving or thinking about bonding and enthalpies that we'll get into this semester. So that's the general chemistry part. That's pretty much our entire semester. So Chem 141, we're focused on the general chemistry aspect. Next semester, if I can entice you to stick with me, there's organic chemistry and biochemistry are the core pieces of that 142 course. And again, it relies on you having a decent general chem knowledge, which I'm sure any of you taking this year with me will have a great foundation on which to build. And then we'll look at organic chemistry, which is probably an area that a lot of you will be more comfortable with. In the sense of it's very little math, the areas we talk about in organic chemistry. So it's a little more comfortable for anyone who's not a big math fan. Biochemistry, same deal. It's not very math heavy, although you're dealing with large molecules, and it does get a little difficult to visualize it at times. So we'll do some cartoons and things that make it a little easier to understand biochemistry if you're brave enough to stick with it for Chem 142. Okay, so right at the beginning of this lecture, I mentioned that alchemy is really our start as chemists, and the alchemists were the pre-chemists. Some of the things that they were after were a little fantastic, and not only have we not achieved them, we can't achieve some of those goals, although we could turn lead into gold now. It costs quite a bit more than just getting the gold normally, and you wouldn't make many atoms of it, but theoretically it's possible. So in addition to looking for elixirs of life and turning lead into gold, the alchemists really did a nice job of figuring out a few important chemical concepts. In particular, they learned how to extract metals from ores. So you were able to refine the ore and get the metal out. And we've known certain metals for a long, long time because they occur naturally as metals, like gold or silver, but other metals have only been made in more recent times, things like lithium and sodium, because of the chemical knowledge we've gained from the alchemists and our own extensions. A lot of the early laboratory equipment was the result of alchemy and alchemists coming up with ways to cause these reactions to happen. You had to have vessels that could withstand high temperatures, for instance, and a lot of the early lab procedures were developed by the alchemists. The big distinction, at least the one who's credited with being the father of chemistry, Antoine Lavoisier, his insistence on careful measurement is really what distinguished chemistry from alchemy. Alchemy was a pinch of this and a dash of that, and they were a little more detailed recipes than that, but a lot of them were in code. A lot of them were never meant for anyone else's eyes. Sir Isaac Newton, who many of you might think is one of the most important physicists who ever lived, actually spent most of the rest of his career, after he got upset with the scientific review process and peer review of publications, he stopped working in physics altogether and spent almost his entire later life working in alchemy. And some of the things that we found, Newton's desk was opened after an auction, and they found a lot of these alchemical symbols. We have no idea what he was doing, probably making some important discoveries, but because it was secret and because it wasn't always done in a reproducible way, that's where alchemy differs from modern chemistry, where we do things carefully with careful measurements and communicating our procedures to our colleagues. We see a picture here of Paracelsus, one of the most famous early chemists, and he's the one not only who believed that the chemicals and minerals could be used as medicines, but his famous quote was, "The dose makes the poison." So things that might be harmless or even helpful in small amounts could often be very dangerous in large amounts. Okay, so getting a little more specific than my earlier definition of chemicals as stuff, which is true, they're the stuff of the universe. We tend to want a little more informative definitions. So if you think about chemicals as substances that always have the same composition and properties, for instance, table salt, sodium chloride, whether it's table salt here in the US or table salt someplace in Europe or Asia or Australia, that's always going to be sodium ions and chloride ions in that 1-to-1 ratio. Everything you see, like I said, chemistry is stuff, chemicals are matter, so if you can see it and touch it and taste it and smell it, then it's probably a chemical in nature, right? Certain things like energy, like wavelengths of light, you can see the light, but the light itself is mostly energy, although it does have that dual particle nature we'll touch on later in the semester. And then finally, chemicals can also be called substances and described as a specific type of material. So if you have that grain of salt, that sodium chloride crystal, for instance, that's a pure substance. It's all the same throughout. If you have a big piece of concrete that has large chunks of rock in some spots and then small fine sand in other parts, it's still a specific type of material, but it's different throughout. It's what we call a mixture of substances. And so here we see a picture of some common toothpaste. Chemistry involves things that we use every day. Better living through chemistry was the DuPont motto there back in the 70s. And it's true. We have come a long way, and we do enjoy a very high quality of life, modern life, because of the result of our knowledge of chemistry. We won't do a whole lot that will help you with the shampoo bottles for this semester, but if you do take 142, you'll have a much better idea of a lot of those names on the ingredient list for the shampoo bottles. We'll talk about things like sodium chloride and some very basic naming rules this semester, but next semester is when we get into the exciting things. But certainly, if you're like me and you like to turn the bottle around and see what's in there, most of the time you may have trouble saying some of those things, but through this semester, through next semester, if you stay with us, you'll have a much easier time and a better understanding. So shampoo, soap, toothpaste, just a few of the things that involve chemicals in daily life. And here we see a table of some of those chemicals commonly used in toothpaste. So calcium carbonate, which is used for chalk. It's also seashells are largely calcium carbonate. So it's an abrasive. It's what helps get that plaque off of there. Sorbitol prevents the loss of water and therefore prevents the hardening of the toothpaste. It also gives a little sweetness to it. You don't want to add sugar to toothpaste because obviously that defeats the purpose of brushing the teeth. But sorbitol does have a nice sweet flavor to it without encouraging the growth of bacteria with sugars. Sodium lauryl sulfate or sodium dodecyl sulfate is used to loosen the plaque as well. That's a surfactant, a soap as it were, slightly different soaps and surfactants, but we won't worry about that distinction yet in this course, maybe next semester. Titanium dioxide is what makes it nice and white and opaque, so it's what we're used to looking at as toothpaste. Titanium dioxide is a very hypoallergenic substance. Not too many people have problems with it, and it's present in a lot of things as pigments to make things look nice and white. Triclosan is an antibacterial agent, and it helps to prevent those harmful bacteria in our mouths that can cause plaque or gum disease. Sodium fluorophosphate prevents formation of cavities by strengthening the enamel. Fluoride in particular, hydroxyapatite is what we ordinarily have in our teeth. Fluoroapatite is even less water soluble. It's even more resistant to decay, so having some fluoride ion present, either as the sodium fluorophosphate or sometimes just sodium fluoride in very small amounts, is helpful to prevent tooth decay. And finally, methyl salicylate gives toothpaste that pleasant wintergreen flavor. That's a lot of us like. Some people might prefer a bubble gum or another type of flavor, but the standard adult toothpaste typically has some sort of wintergreen or mint type flavor, and it's often methyl salicylate that's responsible. So these things may sound off-putting, but they're really common and mostly harmless chemical substances. Alright, so with this little segment coming to a close, let's see how we do with our learning check here. So list 5 chemicals you might find right in your own kitchen. And again, we can be talking about the foods and the beverages, or even the materials that are used in the kitchen itself. We have a few pointed out, so these aren't fair. Make sure you come up with 5 others. But the natural gas, if you happen to use natural gas for your stovetop cooking, it's clean and cheap and efficient way to cook. So that's mostly methane, a little bit of ethane in there. You've got the natural polymers and formica or solid surface countertops, or certainly in quartz or granite countertops as well. Metal alloys in the stainless steel fridges, or even regular painted fridges will have metal alloys as well. Silicon dioxide is the principal component of glass. If the water is chemically treated, certainly at the water treatment plant, or even if you have a filter right at the tap or somewhere in your house. And finally, we see some fruits grown with fertilizers and pesticides. So hopefully this gets you thinking and maybe coming up with some ideas of some everyday chemicals you have right in your own kitchen. Okay, so you certainly might have different lists than what I have here on the screen, but a few examples that are possible to find in the kitchen. We've got calcium carbonate. If you have a marble countertop in your kitchen, you have to be a little bit more careful with that because it does react with acid, so just be careful with the cleaners and the foods that you allow to stay on the surface there if you do have a marble countertop. Granite, not so much a problem. It's not reactive with acids like the calcium carbonate is. Sodium bicarbonate is the principal component of baking soda. And that's a common staple in most kitchens. Sugar, which is the common name for the specific disaccharide sucrose that many of us like to put in our food and drink to give it a nice sweetness. Salt, table salt, as it's commonly known, is sodium chloride. And hopefully yours has a little bit of potassium iodide added. If you're using iodized salt, that does help to prevent iodide deficiency. So in addition to the sodium chloride, you probably have some potassium iodide there. And then finally, for this list, we have acetic acid, which is the acid found in vinegar. Vinegar is mostly water, but it's if you have the distilled white vinegar, it's probably 5% acetic acid. And there's certainly acetic acid in red wine vinegar or apple cider vinegar as well. So by all means, if you want to reach out to me, check your list with me, send me an email. I'm certainly happy to look those over. I would be surprised if you came up with this exact list of 5, but certainly you've got many, many other substances in your kitchen, things like baking powder that have some aluminum sulfate in there, lots and lots of different interesting chemical substances, pure substances, or mixtures in the kitchen. So the main goal here was to get you thinking about how chemistry is everywhere and chemicals are an important part of life, and hopefully you are eager to learn more in our next installment.